There is one more footnote with regard to this excellent theory of locomotion of everything and anything. By the way, it also applies to vehicles, not just animals. We'll get into these vehicles later in the course. It is that every time you have an idea that's a very good idea, and you compare it with the facts. Most of science today is about the facts. They call it data, data, yeah, there's a cloud of, for example, the prediction log of the speeds of things versus body size. Remember, there's a straight line. This is the theory with a slope of 1 to 6, meaning speed proportional to body mass to power 1/6. And then the measurements of everything from tiny, tiny birds to big birds, they kind of crowd around it's the same with the runners and the same with the, meaning one hot dog on its own stick for flying, for flyers, another hot dog for, let's call it for fish. So that's flying. And this is for swimming. And here's the hot dog that accounts for the diversity of movers that agree with the theory, okay? Same with the flyers. And in between, I don't have room because these two hot dogs are almost touching. There's the hot dog of the runners, the terrestrials. And, but every such comparison between the theory and the facts, the data, is accompanied by stragglers, examples or data that are not even in a cloud. So let's think about runners now. With the theory here and all the compatriots agreeing better or not as well. But there are some stragglers. For example, here, meaning, and you've heard these things, the fastest animals like the cheetah, that's a so-called outlier. So the ones that are off or outside the cloud, outliers, meaning lying outside the expected range. And what about those, why outliers? With the cheetah, it's pretty simple. Simple because along with a couple of students of mine, we figured it out. The cheetah is actually not the fastest animal. No. Have you seen cheetah? I have. You have to wait forever until you see a cheetah running. Cheetah is doing two things most of her life. You get the idea here that the word that ends in A in all the Romance languages means it's a feminine word. The cheetah is either asleep or watching for basically an ailing impala that would be easier to catch. So the cheetah is like the jet fighter, belonging to the U.S. Air Force, spends most of its time on the ground. So time average, the speed of the cheetah is exactly on the line. Okay? Yeah. Meaning that when it comes to movement, lifestyle or purpose or mission, objective, plays a role in and is in fact the reason why there appears to be a deviation from the theoretical trend or a diversity of designs. The diversity comes from features other than this trade-off of pushing forward and then pushing upward and then pushing forward. In other words, the so-called life or movement is a much longer story than what we're able to transact here. So yes, what about these? The most famous outliers, meaning people who disagree with the theory, are the most famous, the flea and the grasshopper. They jump. They jump to, meaning with speeds much greater, to distances that appear to have nothing to do with the ordinal. So what about, grasshoppers and fleas? These two cover a fairly wide range of body sizes. I don't know, it's easy to catch a grasshopper, not that easy to catch or even see a flea. Grasshoppers and fleas, and the same sort of spring-like action, the jump, is observed in other domains. For example, in water, there's a species called spiny lobster. The design of these small things is one that involves a bony organ that is it's elastic, it's bent, and then meaning it is loaded with spring energy, spring due to compression or extension. And then when that elastic item is released, then it propels the body forward to a finite distance, just like the boat on Monday. That's distance proportional to the original spring energy stored in the spring. And can we say something predictively about this kind of locomotion? So it's called store and release energy locomotion. On land, the effect of gravity is evident. The model on which my next few things will be based is consists of here's the body size of so many micrograms, and the spring that will be propelling this capital M forward has been compressed, meaning displaced downward against its spring constant K to a distance of the same order as the body length scale belonging to the animal. So the beginning of the attempt to say something is that before the motion will be upward when this spring extends itself. Before that, there's a kinetic energy inventory of size 1/2 K, and then the displacement squared. You learn these things from when they teach you in mechanics about the spring deformation and the energy storage.
Wouldn't that be potential?
Louder?
Wouldn't that be potential energy when it's like stored in the spring?
You can call it that, but you have to do work. Yeah, sure. It's yeah. You use your own language for these things, but the one I know is this one. All right. So let's see now. And then So the so-called latch would be here that holds the body of the animal in place, and then when the time comes, the latch is removed, and the body M is propelled upward with the speed v. So the initial kinetic energy of this mass going up would have to equal the energy that was imparted to it. So 1/2 mv squared has to be the same as 1/2 klb squared. This in my notes is called equation number 2. The first equation would be, never mind, I think this is pretty obvious now. So that's equation number 2. On the way up, the propelled body interacts with the ambient of density rho A. And by the way, you know already that the mass of the body is the density of the body, and then this body length scale to power 3. Most of these equations you've seen already. Going up, the movement is decelerated by the drag force between the body and the ambient. The drag force is F of the order of drag coefficient, frontal area, which is LB squared, and then 1/2 rho of the ambient, and then V squared. I say A here for ambient because soon enough I will claim that this ambient could be air or water. Why not do a theory for spiny lobsters at the same time? All right, let me see what else. And more than once we dissected what's inside this coefficient, drag coefficient. If the speed is high enough, then the Reynolds number is greater than about 100. Then the drag coefficient is a constant of order 1. That's the first assumption I make. And after that, I manipulate all these equations. And of course, I'm waving my hands. Waving my hands means that I did the analysis here. You can do it yourselves, meaning you eliminate a few of these things to arrive at something much simpler. This kinetic energy is destroyed by overcoming this force upward to a travel height called x. So the equation I did not write. So it's end 1/2 mv squared will have to be fx, which in my case is called, I did not even write it. Anyway, but that's basically what it is. So then combining all these things as if commanded from above, you get a very simple formula that the distance of a jump is the body length scale times the ratio of the density of the body divided by the ratio of the ambient. This is simple mechanics. There's no optimization or whatever of anything here. It's just how hard the animal worked on loading its spring. And the jump, in this case, is up to this kind of thing proportional to body length scale, and then this ratio, I already wrote that the density of, if it's air, it's 1 kilogram per cubic meter. The body itself is, I don't know, insects. Insects tend to be not as heavy as if they were filled with, say, what the worm is filled with. Anyway, some 100 to 1,000 kilograms per cubic meter. And now you see why the jump far exceeds the dimension of the jumper. The extraordinary ability of these insects to jump, this is not flight, this is jump, has to do with the simple mechanics of what happens after the release of the spring. Now, the assumption that the Reynolds number is bigger than 100 might be reasonable for a big grasshopper, but for the flea, it certainly fails. And so if you repeat the same analysis, for Reynolds number less than 100, in that case, the drag coefficient is proportional to 1 over the Reynolds number, which means 1 over Reynolds number means V, and then LB over the kinematic viscosity of air. And you get a similar result for the, so I am not repeating this. This will be in an article that I'll share with you that I published 1 year ago. Yeah?
So you mentioned like fleas and grasshoppers.
Would you speak louder?
Sorry. You mentioned fleas and grasshoppers, but would this also apply to like frogs or kangaroos or, other jumping mammals?
I haven't thought about that. And yes, and the basketball players are the same thing, but in their case, their say terminal height, talk about again basketball players, is not due to friction against the air. Their terminal height has to do with somebody said potential energy here, reaching a height, let's call it capital H, where the potential energy here, which is mgh, matches this original energy stored in the spring. So so that would be 1/2 K and then LB squared. So this is a different problem that I'm embarrassed to say I did not think about at the time when I wrote this paper that I'll share with you tonight. By the way, the paper that I will show you is an example of how to communicate with me in your term paper. I don't mean the length of it or the pompous flavor that comes from such a document, but the fact that the way you communicate should be clear, should be complete. It should avoid. It should definitely not confuse me. Okay, and it should look good, so that it is not repulsive. All right. And the result for the flea, so fleas, is similar to what's up here. What is not the same is the corresponding result and about the big things such as the spiny lobster, meaning belonging to this first assumption, that jumps against its own medium, which is water, meaning for the spiny lobster, the ratio of two densities is over 1. So the aquatic jump would be to a distance of the same order as the body length scale. You may have seen these things in the water tank or at the museum. You see some big tanks full of sea creatures. that some of them propel themselves in step-like fashion. They blow water, or anyway, as if a jet relying on the force of reaction. Anyway, they don't go far. They go forward to a distance that is of the same order as the length scale of the motor that pushes the body. So the so-called aquatic grasshoppers, meaning the ones living underwater, do not jump far. They actually jump short, and the shortest distance is the body length scale. I hope with this example you see that what's needed when you run into a theory that claims that it discovered America. It's relatively easy it's a lot more difficult to question a theory, but they're relatively easy to answer your own question. And the message to you is to question and then have fun with your own idea.